Alright, so Mrs. Howard Chemistry, part 4, chemical bonding. This is Unit 6, chemical bonding, Lewis dot structures, naming compounds, and writing formulas. And we still have what the state of Texas says you're going to have to know. Again, you're going to have to name the compounds, you're going to have to write the formulas, you'll have to construct electron dot formulas, you'll need to explain why metals have their properties they do, and you're going to have to predict some molecular geometry. So let's get to the next type of bonding. We talked about covalent bonding. We talked about ionic bonding, where they transfer electrons, and now we talk about metallic bonding. And metallic bonding is when you have bonds between metals, and it's really kind of strange. It's actually caused by the attraction of the metal atoms to the sea of electrons that's around it. And that phrase, sea of electrons, seems to show up on the tests quite a bit, so I'm using that again. And what's cool about it is that the bonding is really strong because you've got this swarm of electrons all around there. And the bonding's pretty easy. The attraction's kind of even all the way throughout, so the bonding's pretty even all the way throughout. It's the same in all directions, same strength in all directions. It's not like we have a polar or a non-polar where it's got, it's not like we have a polar where one side is more negative, it's attracting the electrons more tightly than the other. So basically, you have these valence electrons. They started off with their own atom, with their own nucleus, but they didn't stay with them. So these valence electrons, they're partiers. They're moving around, going to whichever atom they want to go to. Okay, in metals, okay, do you remember the SPDF? S, P, D, and F, the shapes of the orbitals. And we have groups 1 and 2 are in the S block. That means the last valence electron I stick in there is going to be in an S orbital. Way over on the right-hand side, most of the non-metals are the last. I don't know what's happening here. Why does this do this to me? Let's just ignore it. Maybe it won't pop up again. Okay, so the P block is over there with the non-metals, and then that big center in the middle is the D block. And that means the last electron I put in there is typically going to be in a D orbital. And they're big orbitals. Well, that means most metals, their P and D orbitals are big, but not that many electrons are in there. And what happens is those outside big, humongous orbits that are mostly empty tend to overlap. And that's what allows those electrons to hike from one atom to another, just kind of sporadically go from one atom to another throughout the whole entire metal. That creates great conductivity of heat and electricity. Small distances between the orbitals allows for lots of different photons to be absorbed. So once you have all these overlaps, you've got lots of different photons that can be absorbed easily and then re-emitted easily to form the light in the form of light. So we see that as shiny. So we've got its luster, we've got its great conductivity, and since the metallic bonding is pretty much even in all directions, they don't break easily. That means the metals are malleable, so we can hammer them into flat sheets. They're ductile. We can pull them into thin wires. And they have really high melting and boiling points, especially compared to the ionic and the covalent bonds. So we've got the third of the 3 types of bonding, the metallic bonding. Oh, and that was really short and sweet.